In this section, we're going to learn about Rust's killer feature, ownership and the borrow checker. So first we're going to start out with some motivation for the borrow checker, because if you come to Rust without really understanding why the borrow checker was needed, it can seem kind of like just a needless pain, but really it's very, very important. So much of Rust's unique power comes from its system of ownership and borrowing. This crucially eliminates all memory unsafety. Programs written in safe Rust should never segfault. It also prevents data races. So what is memory unsafety? Now, I mentioned segfaulting, segmentation faults. That's when a program attempts to access memory that is outside of its allowed area in the virtual memory space. However, Rust is also able to prevent with a combination of very strict static compile time checking with the borrow checker and a tiny bit of extra runtime code, which really doesn't affect performance noticeably. It's able to prevent segmentation faults, buffer overruns, that's where you read off the end of an array, so you have an array of, say, 10 elements and you attempt to read the 11th or 13th, dangling pointers, that is, functions that return pointers that were pointing to their stack, so the memory is freed after their stack is popped, and the pointer still sticks around and people try to access it, so it points to somewhere random on the stack. Double freeze, meaning you allocate some memory, then free that memory, and then later you free it again. And this is going to cause all kinds of issues up to and including revealing sensitive information or just causing your program or even your whole operating system, in the case of older operating systems, to crash. And use after freeze, which are the big one for security. Modern browsers, most of the security flaws that are found are actually going to be use after freeze, and they can be absolutely devastating in terms of security impact. So Rust is going to totally eliminate those as well. So what about garbage collection? Garbage collection does in fact solve the memory safety problem, but it imposes a significant performance overhead. Every certain amount of time, the program has to stop and collect garbage, or it can happen as a fairly constant overhead during program runtime, and this is just going to cause you problems if you need that extra performance. Rust's static compile time checking imposes no runtime penalty, and even in the case of the few runtime checks that it does, that penalty is extremely minimal. The other big one is concurrency. Now, concurrency is a huge deal. It can contribute massively to performance and efficiency of your program. It can increase the responsiveness of a graphical user interface, increase the throughput of a server, increase even the compute performance of heavy math applications. And modern processors have tons of cores, even consumer processors. So what Rust's community calls fearless concurrency is a big deal. A complete defense against data races, that is, situations where one thing is reading from a piece of memory at the same time as another thing is writing to it, or two things are writing to something at the same time, makes concurrency much, much easier to implement. It allows you to take better advantage of modern multi-core systems without worrying about, oh, is my program going to crash? Are the results going to be wrong? Are they going to be inconsistent? How can I test this? You can test it. It will work out. In Rust, the borrow checker ensures that you do things right and prevent data races.